All right, let's pull back the curtain on one of the most critical yet kind of mysterious parts of our modern world, the electrical substation. We're going to take a journey inside and figure out what all that buzzing equipment actually does to keep your lights on. You've definitely seen them, right? Those big fenced-off yards just humming with all these crazy steel structures and giant metal boxes. They look super complex, maybe even a little intimidating. But what's the real story? How does the power for your life get through that maze? You know, at its heart, a substation really only has two main jobs. First, it's a translator. It has to change the voltage of electricity. And second, it's traffic cop, telling all that power exactly where it needs to go. If you can remember that simple idea, everything else we're about to talk about will make perfect sense.
So how do you organize one of these things? Well, it's definitely not random. Every single piece of equipment is placed with incredible precision. The layout itself is a high-stakes game of engineering.
The key word here is strategic. This isn't just about Tetrising a bunch of equipment into a space. Substation layout is a super deliberate plan to make sure the lights stay on, to keep workers safe, and to make the whole system run like a well-oiled machine.
Every single design decision comes down to these four golden rules. Is it safe? For the public, for the engineers, for everybody? Is it reliable? Will it deliver power without a hitch? Can you actually operate and maintain it easily? And maybe most importantly, can we expand it in 10 or 20 years when our power needs grow?
Okay, let's actually follow the path of electricity. We're going to start right where it makes its grand entrance into the substation from the wider grid.
So you know those massive power lines you see stretching for miles across the country? Those are the superhighways of the electrical grid carrying insane amounts of energy. The substation, well, it's the critical on-ramp and off-ramp for these highways.
So, how do you get all that power from a wire dangling way up in the air down to the ground safely? You use one of these, a gantry. This is basically the first thing the electricity meets once it's inside the fence. Think of it like a giant, super sturdy coat rack for high-voltage wires.
But a gantry is way more than just a simple frame. It's holding up immense tension, and it's the main connection point. Most importantly, it maintains what engineers call electrical clearances. That's the minimum safe distance you need to prevent that powerful electricity from literally jumping or arcing between wires or down to the ground. Very important stuff.
Now let's move into the heart of the substation, where the real magic happens. This is where our translator and our traffic cop really get to work.
And here is our translator. See, the power coming in from those big transmission lines is at a voltage that's way, way too high for your home. The power transformer's #1 job is to step down that voltage to a more usable level, which makes it arguably the most critical piece of hardware in the entire place.
Now, because transformers are so huge and so important, where you put them is a very big deal. You need to leave clear road access for massive cranes to install or replace them. They contain huge amounts of oil for cooling, so you need dedicated fire protection and containment systems just in case. Their sheer physical weight really dictates a lot of the substation's layout.
All right, on to the traffic cop. There are basically two main ways to build the equipment that directs the flow of power. The traditional way is air-insulated, which is what you're picturing in your head, those big, sprawling outdoor substations. But the more modern, compact version is gas-insulated.
Let's focus on this modern approach for a second. Gas-insulated switchgear, or GIS for short, takes all the control parts, the switches, the circuit breakers, and seals them up in a metal tube filled with a special insulating gas. And because of that gas, you can put everything much, much closer together.
So using GIS lets engineers squeeze an entire substation's control system inside a single building. This is a total game changer for dense cities where land is super scarce and expensive. It's also safer and more reliable since all the important bits are protected from the weather.
Okay, so the power has arrived, it's been translated to a lower voltage, and it's been directed by our traffic cop. So what's the final step before it heads out to our homes and businesses? This is the last checkpoint, the medium voltage switchgear. If the GIS is the main highway interchange director, think of this as the local traffic controller. It takes that medium voltage power and splits it up, sending it out onto the specific power lines that run right down our streets.
And just like everything else we've talked about, the layout here is absolutely key. This equipment generates heat, so it needs good ventilation. It has to have safety screens to protect the people working on it. And of course, engineers need clear, easy access to every single circuit so they can manage the local grid effectively.
So, as you can see, a substation is so much more than just a jumble of parts. Let's zoom back out for a second and see how this all comes together to form one amazing system. So let's do a quick recap of our power's journey. It gets welcomed by the gantry, translated by the transformer, directed by the high-voltage switchgear, and then managed for local delivery by the medium-voltage switchgear. Each component has a really distinct and vital role in that sequence.
You know, this quote from our source material really says it all. The true genius of a substation design is this constant balancing act. It's a puzzle of safety, efficiency, security, and planning for what's next, all solved in steel and concrete.
So the next time you drive past one of these places, don't just see a fence and some metal. See it for what it is. A highly intelligent, carefully choreographed dance of physics and engineering. It's a system working silently, 24/7, just to keep our entire world running.
And that leaves us with one final and really critical thought. As we start plugging in millions of electric cars, building these power-hungry data centers, and trying to integrate fluctuating renewable energy, well, the demands on these gatekeepers are going to skyrocket. So how do they need to evolve to handle that new, complex energy landscape? That right there is the next great engineering challenge.